It's my pleasure to introduce today's, how to say, we'll give this seminar talk today. It's Duvan Cardona from Colombia. He studied in Colombia. Got his bachelor diploma there, and then worked in Colombia, in Bogota, at the university, until 2018. After 2018, he arrived to Belgium, and after that, he works in the group of Professor Różański, where I met him, and he was recommended by Professor Różański for the talk, and it's my pleasure to give him word now, and I think it will be interesting talk for us. Duvan, you can start now.
Thank you very much, Professor Dudu Chava. Indeed, it's my pleasure to be here, to be part of this seminar. The talk today is about oscillating Fourier multipliers theory. I will talk about the geometric aspects and the role of the symmetries in the case of Lie groups when I studied this, the boundedness of this kind of operators. So the results that I will report are part of my joint work with Professor Michael Różański. So here you can see the main keywords of the talks: singular integrals, oscillating singular integrals, and zero differential operators. These are the operators that we are interested in studying, in analyzing. And we are interested mainly in studying the boundedness properties of these operators on LP spaces, on sub-LP spaces, and spaces that are that plays an essential role in analysis and geometry, and also in PDE, like trivial circular spaces, best of spaces, and etc. So here, let me just make an short historical remark about the theory of singular integrals. You can see here some the first page of some of the fundamental papers in the theory. Here you can see, for example, the classical paper of Calderón, Alberto Pedro Calderón, a mathematician from Argentina, and Calderón-Zygmund, a paper that appeared in Acta Mathematica that was dedicated to Professor Malzer-Ries. And this paper was published in 1952. There, Calderón and Zygmund introduced a general study of singular integrals. In this case, they considered here convolution, the case of convolution operators. So they consider a linear operation of this form. And the main motivations for them was to generalize, to consult a theory generalizing the Hilbert transform. The Hilbert transform. So this is one of the fundamental papers in the theory of singular integrals. In the words of Elias Stein, in one of his manuscripts about the history of singular integrals, Stein says that this is probably one of the more fundamental papers that were published in analysis, with that very big influence. After here you can see another paper about, also published in Acta Mathematica by Charles Fefferman. This paper is about boundedness also of singular integrals, but of oscillatory type. So the prototype of the example in the case of the one-dimensional example, in the case of the Calderón-Zygmund operator, is the Hilbert transform. But in the case of, in this paper of Charles Fefferman, he concentrates his analysis in the case of oscillatory singular integrals. These are mainly convolution operators. You can write, one can write in this form, convolution operators, in such a way that the Fourier transform of the kernel has some term which has polynomial decay, like this. but also has one complex exponential term. Okay, so this is the prototype of the operators that are studied in the setting of in the theory of Charles Fefferman. This was a problem that to study the boundedness of this operator was a problem that Stein proposed to Charles Fefferman, and he made big developments in this paper. And after that, okay, just let me add that in the case of these operators, the effort in this paper of Fefferman was to study the weak 1-1 boundedness of these operators, of these oscillatory operators. And later, in another paper that Fefferman published with Stein in 1972, probably, about Hardy spaces of several variables, they extend the weak 1-1 estimates by Fefferman to the case of the Hardy space. These were one of the main applications that they obtained in this paper, fundamental paper. Here you can see another paper, another work, very fundamental work in the theory of singular integral that was published by Hormander, also in Acta Mathematica, probably in 1960. And in this paper, Hormander studied integral conditions for the boundedness also of convolution operators. I will talk about the condition that Hormander introduced in this paper for the boundedness also of convolution operators. These are indeed, by the structure of Rn, these operators are translation invariant. And it's fundamental, it's important to mention that before that the work of Calderón and Zygmund about the boundedness of singular integrals, Solomon Miklin was made fundamental contributions to the theory also. Here you can see the first page of the work of Solomon Miklin that was published in Russian Mathematical Service. Okay, all of these 5 papers that I have present here are about singular integrals, all of these about of convolution type, but the last one that also is important for our interest is that one can consider also operators which are not translation invariant, and then these operators are, for example, pseudo-differential operators, and the boundedness properties, sharp boundedness properties for these operators were studied in a very famous paper by Charles Fefferman that was published in 1972, probably in Israel Journal of Mathematics. So that I want to share with you is the first page of these very fundamental papers. Every of them introduce very important techniques. And here, let me present the picture of these big mathematicians. I saw now Professor Gergrup here, who maybe new in person to Lars Hormander. Here you can see also Charles Fefferman, Elias Stein, Alberto Calderón, Anthony Zygmund, and Miklin. So it's my pleasure today then to talk about this topic, which is very relevant in mathematics, but maybe with more modest contributions than the contribution of these big mathematicians. So which is my goal in this introductory talk? Is the following, is to present the extension of the boundedness of singular integrals in the case of Lie groups of polynomial growth. Of course, the conditions that we will present are conditions in the spirit of the condition of Hormander and Calderón and Zygmund. And that we did was to try to generalize in this setting the theory of Fefferman and Stein, yes, using Fourier transform on these groups when it is possible, and also using kernel conditions. This is maybe the main goal. Here we will consider Lie groups of polynomial growth because we have many examples that are relevant for analysis. For instance, you can see big examples, natural examples, and important examples of compiled groups are the torus, SU2, which is diffeomorphic with the sphere in R4, SUN, etc. Also, we cover, our analysis cover the case of nilpotent Lie groups, like the Heisenberg group, and also a big class of Lie groups, which are called graded Lie groups, which are homogeneous Lie groups, where you have there one graduation of the Lie algebra, and you have one system of dilations that are acting on this Lie algebra. So on this big class of homogeneous Lie groups, there are specific operators which are hypoelliptic there, which are Rockland operators, and in terms of the symbol of these operators, we will present some criteria for the boundedness of singular integral. This is that we will report today. So the motivation to do this, like I mentioned before, is that we have Lie groups. In Lie groups, we found manifolds, which are manifolds with symmetries. We can explore in a big part of the class of Lie groups a very fundamental tool, which is the Fourier transform. And there we can give conditions for the boundedness of singular integrals in terms of the sub-Riemannian structure of one general Lie group of polynomial growth, or in the case of graded Lie groups, we can give criteria in terms of Rockland operators, which are hypoelliptic operators with arbitrary order, which are left invariant and positive if you want. Okay, so let me continue with the talk, maybe with more details. I will present some definitions. So let me review first the case of Rn. Okay, so let's consider the space of distributions on Rn in the sense of Lagrange bars. So associated to one distribution on Rn, you can define one convolution operator in the natural way using the group structure of Rn. Yes. And then you can define this convolution operator T associated to this kernel K, and you can define these convolution operators in the space of test functions. So the spirit in the study of the boundedness properties of convolution operators, and that motivates one of the fundamental problems, is which properties on the kernel gives you the boundedness properties on the operator. Okay, and for instance, one can consider boundedness properties of these operators on Lebesgue spaces, yes, which are fundamental spaces in analysis. Here, I just wrote the definition of the LP norm on Rn. Okay, so there are fundamental examples, of course, in the case of Rn of convolution operators. And it's very important to mention that in the case of Rn of other groups, one can classify the L2 boundedness of convolution operators using the Fourier transform. Yes, so you have here one convolution operator, and it's very well known that this convolution operator is bounded from L2 to L2 if and only if the Fourier transform of his kernel is a essentially bounded function. Yes, it's a function in L infinity. Here, I recall the definition of the Fourier transform, yes, which you can consider initially in many domains, but it's a very well mapping from the Schwarz class to the Schwarz class. Here the definition of the Schwarz class. So, like I mentioned before, here you can see the classical argument that proves that if one convolution operator has a kernel K such that the Fourier transform of the kernel belongs to L infinity, then the operator is bounded on L2. Here you can see this is the classical argument using the Plancherel theorem. Okay, so this inequality that I wrote here just says you that the norm of the operator, like a bounded operator on L2, is less than or equal to the L infinity norm of the Fourier transform of the kernel, but a careful analysis shows that this indeed is one equality. Very well. So the following is the fundamental question of this talk: is can we use the Fourier transform to analyze the LP boundedness with P different of 2 for convolution operators? And the answer is yes. For example, like in the works of Fefferman and Stein that I will present as for. So let me now to talk about the LP boundedness of convolution operators. Let me present some results by Calderón-Zygmund and Horman. So when talking about the LP boundedness of convolution operators, one of the main motivations arise at the beginning of the past century, where Marcel Ries proved the LP boundedness of the Hilbert transform. You can see here, the Hilbert transform is this operator, is this convolution operator on the real line, acting on functions on the real line. And a very beautiful theorem by Marcel Ries that he proved in 1927 says that this operator is bounded on LP. This operator is important in the study of the summability of the Fourier transform in the case of Rm. One can say summability, yes? But Kolmogorov also in 1925 proved that indeed the Hilbert transform is an operator of weak 1-1 type. We say that it's an operator bounded from L1 to weak L1. Yes. So here you have the definition of the semi-norm of one function in weak L1. So these two results of one by Ries and the other one by Kolmogorov, then are the starting point to check if there are more operators of singular type that also of convolution type that generates bounded operators on LP. Yes, so a very beautiful condition by Hormander, published in 1960 in Acta Mathematica, says that indeed you can generalize these results that are satisfied for the Hilbert transform. The condition by Hormander says that, okay, you can consider one distribution on Rn and assume that your distribution satisfies these two conditions. The first one is one condition on the kernel. You can see that here in this condition, you are taking the difference of the kernel in two different points. So this is somehow one regularity condition on the kernel. But the second one says that the Fourier transform of the kernel belongs to L infinity. Yes, so this condition is to get the L2 boundedness of the operator, but and also the first condition is somehow one smoothness condition, okay? Smoothness condition. So what Hormander realized was that these two natural conditions in some sense are enough to say that the convolution operator associated to this kernel is of weak 1-1 type, okay? And more than that, Hormander also proved the LP boundedness, yes? Because if you have the weak 1-1 inequality for this operator, you can use that this operator is bounded on L2. You can use interpolation to say that this operator is bounded on LP for every P between 1 and 2. And after that, you can use the duality argument to extend your result to your boundedness result for P larger than 2. Okay? So this is the starting point, these Hormander conditions. Examples of kernels satisfying the Hormander conditions are the following. You can consider, for instance, one distribution on Rn, which has one bounded Fourier transform with a kernel satisfying these two growth conditions. This is this here that says that the kernel has a singularity of order minus the dimension, but when you derivate, then you will decrease the order of your derivative. Probably here is +1. Yes, here is 1. So with these two order for the singularities of one kernel and the gradient of the kernel, one can see that indeed this convolution operator satisfies these two conditions by Hormander, yes? Which looks more natural because, for example, it's very easy sometimes to check if the gradient of one distribution satisfies this kind of growth. So then, in view of the Hormander's criteria, here you have one convolution operator satisfying these conditions here. Then you will get not only the LP boundedness of this operator, but also the weak 1-1 boundedness. So another that is probably one of the fundamental applications of the Hormander condition is this condition of Hormander-Milling. Using the theorem of Hormander, one can check, and indeed one can see that one Fourier, that one convolution operator with kernel K, such that the Fourier transform of the kernel, which is the symbol of the convolution operator, if this symbol satisfies this growth condition for the derivatives, then the Hormander-Milling condition is called this. Then here you have the Hormander-Milling condition, your operator is bounded on LP, and also for P between 1 and infinity, and also of weak 1-1 type for P equal 1. So there are many examples of kernels that are not in the scope or that cannot be studied in the theory of Calderón and Zygmund. For example, this is one example of Stein. Check the following example, please. You have your operator. This is a convolution operator. But check this kind of kernel. This kernel here. This is a kernel that has somehow one polynomial decay, but also have one extra term which is of exponential type and complex exponential type. So this kernel has satisfied these two properties. Yes, that the Fourier transform decays in this way. This is far from, this is not, okay, this just says that the operator associated to this kernel is bounded on L2. But when you check which is the regularity condition for the kernel, is not exactly the Hormander condition. It's another kind condition. Yes, a condition which we call oscillating, for example. This is not, this is more general condition than the condition of Hormander. So this is one example of one convolution operator that is outside of the Calderón-Zygmund theory. But before of 1970, it was very known that this operator was bounded on LP, okay, for P between 1 and infinity. But for P equal 1 was unknown something about the boundedness of this operator. And then Stein proposed the problem to Fefferman to prove that this is indeed one operator of weak 1-1 type. So, surprisingly, Fefferman in 1970, in a paper, in the paper that I showed you in the introduction, proved this very beautiful theorem in Acta Mathematica. Fefferman proved that if you have one distribution, you can assume that your distribution is locally integrable, far from the origin, and you fix one parameter theta with theta between 0 and 1, theta different of 1. And here you have these two conditions here. The first one is the decay of the Fourier transform of the kernel. You can check. Here, this says that the symbol of your convolution operator has this order, minus n theta over 2. This is somehow the order of the symbol of your operator. And here you have this oscillating Hormander condition. We call it oscillating because we have the presence of this factor here, which is 1 minus theta. With theta equal 0, then we are in the case of the Hormander condition, but with theta strictly in the interval between 0 and 1, this is another and more general condition. So that Fefferman proved that was with these two properties on the kernel, the first one with the decay of the Fourier transform, and the second is one smoothness condition on the kernel. Your operator is bounded on LP, but for P equal 1, your operator is of weak 1-1 type. And something to say about this result of Fefferman is that he modifies a little bit the composition of Calderón and Zygmund for one integrable function in order to prove this theorem. We know that if we have one L1 function, we can decompose this function in a good part and also in a bad part. And the bad part, you can decompose the bad part in small pieces. These small pieces are supported in bowls, for example, in some bowls. And one important property that satisfies these elements, these small pieces, B sub G, is that they satisfy the the cancellation condition. Yes. And another condition about the growth of these functions in terms of the measure of C supports. Okay. Let's say that the support of these functions are big. So this is somehow the decomposition of Calderón-Zygmund for one integrable function. That Fefferman did was to find replacements for these small pieces, BG, in terms of convolutions for certain specific convolutions functions here that allow to regularize these small functions. And okay, just let me say that one of the fundamental steps in the proof of this theorem was to modify the Calderón-Zygmund decomposition of one integrable function in a very clever way in which Fefferman did. So after that, if you see, the Fefferman theorem gives you the LP boundedness of the operator and the weak one inequality for the operator, but still is open, for example, the boundedness of this operator from the Hardy space into L1. So in a paper, in the paper of Fefferman and Stein in Acta Mathematica, published in 1972, they get that with the same conditions that Fefferman stated in his previous paper, then this convolution operator is bounded from the Hardy space into L1. So summarizing, here you have these two properties. Here you have this decay order for the Fourier transform of this oscillating Hormander condition. You can give the boundedness of your operator on LP, the weak one inequality for the operator, and also the boundedness on the Hardy space on R. So here I am talking about the Hardy space. Maybe all of you are familiar with this notion. Is the atomic H1. You can define this like linear combination of atoms, and these atoms have support on bowls, having some growth, and the norm of any of these functions in L1 is the infimum of the sum of these scalars that you use in the representation of your function in terms of atoms. Okay, so summarizing, I have presented the Hormander condition and the generalization that Fefferman and Stein and Fefferman give in two papers in Acta Mathematica for this Hormander condition. So examples of the convolution kernels in the Fefferman and Stein settings are the following. First, let me show you the previous example. The previous examples I mentioned is to take this kernel, and then this kernel satisfies these two inequalities here that you can see. Mm-hmm. These two conditions with theta equal half. Okay. And another examples that are more important, maybe because you can parameterize with very nice constants, very nice parameters, are the operators that, in the case of Rn, one call oscillating Fourier multipliers. These are operators that have convolution form in such a way that the Fourier transform of the corresponding kernel has this form. Here you can see some decay, polynomial decay, and you can see one exponential term that is giving you the oscillatory part of this kernel. Here we can consider one cutoff function near to the origin. Yes, and then one can see that this convolution operator is such that the kernel satisfies these two conditions here. So I here present one general the Fourier transform of these kernels in general way, I mean, considering A being positive and alpha being positive also. But in the case of Fefferman and Stein, this needs to be equal. I mean, this is covered by the Fefferman and Stein theory if you have that A is equal to alpha. Yes? Yes. So, summarizing, I have here some examples of oscillating singular integrals in the case of Rn. And now I will move to the case of Lie groups, which is certainly more general, but let me try. So here you can see these are some reference about the subject that we have published with Michael Ruchansky. In these papers here, we have extended some of the results of Fefferman and Stein, and also of Fefferman. In the case of singular integrals, in the case of simple differential operators, and so. And I will talk about maybe about the fundamental result that we have in the direction of the Fefferman and Stein result that I present before. So consider one Lie group. We will talk about the boundedness of singular integrals of convolution types on Lie groups. Let me remind you, you have one Lie group, then that you have is one smooth manifold, where the product of and the inversion, which are the operations that you have on the group, are smooth functions. Yes? Associated to this Lie group, you have the space of distribution, which is the topological dual of the set of smooth functions with compact support. And then this is our space of possible kernel for convolution operators, because to any convolution, to any kernel that belongs here, to any distributions on the group, you can associate one right convolution kernel in this way. Yes? And again, as in the case of Rn, you can associate this convolution operator in terms of the operation of the group. Yes. Here I denote dy, the left half measure on the group. Okay. So our goal is to give shared conditions on the kernel in order to have the boundedness of these convolution operators on LP from the Hardy space into L1, and to have the weak one inequality for these operators. To do that, what we will do is to use, like in the words of Fefferman and Stein, the Fourier transform, and to combine the Fourier transform conditions with the kernel conditions. So one reason to choose Fourier transform on Lie groups, because here on Lie groups, some of them have good representation theory. In terms of the representation theory, you can define the Fourier transform, and this is because you have many symmetries on the group. For instance, you have actions of the group on arbitrary Hilbert spaces, and in terms of these actions, you can define the representation theory of the group. So, for instance, let me consider two cases: the case where the group is compact and the case where the group is not compact. Yes, any compact Lie group is a Lie group of polynomial growth. Yes, because the bowls satisfy that the volumes growths satisfying the doubling condition. So in the case of compact Lie groups, let me introduce the Fourier transform. What you have to introduce the Fourier transform is necessary to define representation on the group. So let me define unitary representations on the group. You have that one representation is unitary on the group if the representation that the function that you call one representation is a map from the group to the space of unitary matrices of order of size L cross L here, L cross L. And if this mapping is an endomorphism, I mean, you have one map from the group to the space of unitary matrices of some complex Euclidean space, you will say that this is one unitary representation if this is one homomorphism, continuous homomorphism between the group and this space. And that you have then is that for any two elements of the group, you have these two conditions, okay? This says that this map psi is compatible with the operation of the group, okay? So you will say that this unitary representation is irreducible if this representation is not the direct sum of any two of other two unitary representations on the group. Okay? So we have now unitary representations. We have now when one representation is irreducible. And that we will do now is to define this set, which is the set of all unitary and irreducible representations on the group. And we will denote this. This is the space of representations. Sorry, here I have. Okay. This is our set of representations. Very well. On this set, we will define one equivalence relation. The equivalent relation is as follows. You have two equivalence relations on the group. You will say that these equivalence relations are equivalent if and only if you can find one endomorphisms A, which we denote here A, and this endomorphisms allow you is defined between the corresponding representation space, but with the characteristic that allow you to obtain the values of one representation in terms of the values of the another one, like here, like in this gray box. Okay, so when you have this equivalently, you have that this diagram is commutative. Okay. So that is important here is that this relation that we define in the space of representation is an equivalent relation, and then we can consider the quotient of the space of representation with respect to this equivalent relation. And then that we get is one, in the case of one compactly group, one discrete set. Yes, one discrete set. So define G hat to be the quotient space between the space of representation and this equivalent relation defined here. This G hat is a discrete space, and any element of this discrete space will denote using the usual nomenclature like bracket psi. Okay. Very well. So if we have one Fourier transform, what we want to define first the Fourier transform, but we need to have the Fourier inversion formula. Is that we have, for example, if one function is smooth. If you have one smooth function, then you can define the you can define the Fourier coefficients of the Fourier transform at any representation. In this case, in the case of compactly groups, the Fourier transform are evaluated in representations. And then, in some basis of the representation space, the Fourier transform becomes to be matrix value. And that is important with respect to this choice of Fourier transform is that we have the Fourier inversion formula, like in the case of Haren or like in the case of the torus. Okay? Because the Fourier transform is taking matrix valued functions, here in the Fourier inversion formula, we have an extra operator, which is the operator trace, which is taking the trace of usual matrices. Yeah. Okay, so we have then on compactly groups, we have the Fourier inversion formula, you can see here. And then the question is if we can study for the boundedness of convolution operators, this Fourier transform associated to the two representations. Because here you have, for instance, here you have one convolution operator, you have one convolution operator like this. When you take the Fourier transform, you will have that the Fourier transform transform convolutions on products. Yes. So we have by the properties of the Fourier transform that the Fourier transform of T of f, where T is your convolution operator, is the product of the Fourier transform of these two functions, matrix-valued functions. And then using the Fourier inversion formula that you have is that your operator admits this representation, this discrete representation. So now the natural question is if we can use the Fourier transform to study the decay of the Fourier transform of the kernel, and if we can use conditions of the similar type, like the condition by Hormander, like the condition by Fefferman and Stein, to measure the regularity of the kernel. To do that, we need to express the decay of the Fourier transform of the kernel in terms of some real numbers. Yes. And these real numbers, in the case of one compactly groups, are the Laplace are the eigenvalues of the Laplacian. So let me present something about the eigenvalues of the Laplacian. Consider one basis of the Lie algebra. Yes. The Lie algebra can be identified with the tangent space of the group at the identity. So you have that your positive Laplacian is minus the sum of these squares of these vector fields. And then that is curious in the theory, in the representation theory of compactly groups, is that the eigenvalues of the Laplacian can be enumerated using the unitary dual. So because the unitary dual is a discrete set in this setting. So if you fix any representation psi, you fix any representation, this is your representation psi, and you evaluate the Laplacian in this representation, you have this identity for some real number. So this says you that the eigenvalues of the Laplacian, the eigenfunctions of the Laplacian are indeed the entries of the matrix entries of this of the representation. And for any representation, for any equivalent class, you have one eigenvalue. So this is okay. This is that one can say about the eigenvalues of the Laplacian. Okay. So to measure the decay of the Fourier transform of the kernel, just let me use the following notation. For any equivalent class in the unitary dual, let me define the Japanese bracket of psi to be this quantity here. Because just let me say that if lambda psi is one of the eigenvalues of the Laplacian, then 1 plus lambda psi half with power half, this will be one eigenvalue of this operator, of this Bessel potential of order 1. So are exactly these eigenvalues the real numbers that one used to measure the decay of the Fourier transform of this kernel. So in terms of the eigenvalues of the Laplacian, and in terms of this Japanese bracket that you can see here, we can state one of the main theorems that we obtained with Michael Ruchansky on this idea is the following. You consider then one compactly group of dimension n, and let us consider one number theta between 0 and 1 in this way, with theta different of 1. And then choose one distribution which is locally integrable far from zero, from the origin in this case. And let's assume that this kernel satisfies these two conditions. The first one is the conditions of the Fourier transform of the kernel. And the second one is the condition that Fefferman studied in the case of oscillating singular integrals. Okay? So here you can see the Fourier transform of your kernel is one matrix valued function in any representation space. So you can take the operator norm of this matrix, and if this operator norm satisfies this inequality here with this growth, this inequality says that the order of your Fourier transform is this one, minus n theta over 2, where n is the dimension of the group, and theta is the parameter that you choose. And here you also have these smoothness conditions for the kernel, oscillating smoothness condition for the kernel, where here appear this parameter 1 minus theta. Then we proved that this operator is of weak 1-1 type, like in Fefferman, like in the Fefferman's theory. Also, we proved that this operator is bounded from the Hardy space into L1, and of course, as expected, using the duality arguments, your operator is bounded on LP for any P between 1 and infinity. Okay. So this indeed is one analog of the theorem of Fefferman, but let me say something about this decay condition of the Fourier transform. This decay condition. Yeah. I present this condition in terms of the Fourier transform because in the case of compact groups we can use the Fourier transform indeed, but there are many Lie groups without a good representation theory and where you can use the Fourier transform. There are indeed many Lie groups of polynomial group where it's not well understood the Fourier transform. So to see which is the analog property of this condition in the case of Lie groups of polynomial growth which are not compact, one can rewrite this condition in terms of the Laplacian. I will show you how one can do this. Because this condition here, this condition here is equivalent, of course, to the following one. But if you use the Plancherel theorem, that this inequality says is that the composition of these two operators are bounded on L2. Okay? If you use the Plancherel theorem. So here. This condition here, this inequality condition, gives you the boundedness of this operator. The L2 boundedness of this operator. So you don't need the Fourier transform to express this condition. All that you need is the composition of your operator, your convolution operator, with one power of 1 plus the Laplacian. In this case, this is the power, minus n theta over 4. Yes? But this is the inequality if you want to say that, if the order of your operator is minus n theta over 2. Where you have 4 by the algebraic properties of these operators and their eigenvalues. So in the case of we have this. In the case of Lie groups of polynomial group, if the group is compact, then we can rewrite the operators, the boundedness of singular integral operators in this way. Yes, you just need that this composition is bounded on L2, and you also need this smoothness condition, okay, regularity condition, and then you will get the boundedness of your operator on L1 into weak L1 from the Hardy space into L1 and on LP. Yes, but maybe I am close to finish the talk, so let me explain a little bit about how to generalize these theorems in the case of Lie groups of polynomial group without the assumption of the compactness of the group. So here that we will use is one sub-Riemannian structure on the group. So you take a non-compact Lie group of polynomial growth. This is, you take one system of left invariant vector fields on one Lie group and assume that this vector fields satisfies the Hormander condition. This means that the Lie algebra is generated by these vector fields and their commutators. And then in terms of this system of vector fields, you can define one distance. And in terms of this distance, you can define neighborhoods, okay? So let me remind you how to do this process. You will say that one curve is horizontal if you can write this curve like a linear combination of the Hormander vector fields of your system. And then you can define the length of this curve in the usual way, yes, using the velocity vector associated to the curve. And then, because you have this curve and also you have that this system of vector fields satisfy the Hormander condition, there is a theorem that says that always you can connect 2 points of the Lie group using horizontal curves. And then you can define the distance between 2 points using the infimums of the lengths of all the horizontal curves that connect your 2 points, okay? So, like I mentioned before, if you have this distance, then you can define neighborhoods there. You can define balls there. And finally, you will say that one Lie group is of polynomial growth if there exist 2 integers here, d naught and the infinity, such that the volume of the balls grows in this way when R belongs to this interval, when R is small. But if R is bigger than 1, the volume of your ball grows like this, in this way, okay? So when we have these two properties, we say that the Lie group is of polynomial growth, and indeed, all this construction depends of the vector of the less invariant vector system that you choose at the beginning. This construction depends on the sub-Riemannian structure that you choose for your Lie group. So one can prove that d naught here, d naught, depends on the group and on the system of vector fields. But also one can prove that, okay, and in view of this dependence, one calls to d naught the local dimension of the group. But an infinity, one can prove also that this quantity, the infinity, this dimension of infinity, is independent of the system of vector fields that you choose. So this is one quantity defined intrinsically in terms of the group. This is related more with the geometry of the group. So, okay, in the case of compact groups, to state the boundedness of singular integrals, we use this composition with the Laplacian, but in general, Lie groups of polynomial growth that we will do is to use Laplacian, because if we have this system of vector fields, then to these systems we can associate one positive sub-Laplacian, which is equielliptic in view of theorem of Hormander, published in 1955 probably in Acta Math. And then we have this theorem with Michael Rochanski about the boundedness of oscillating singular integral. This says, okay, consider one Lie group of polynomial growth here, and consider one system of vector fields satisfying the Hormander condition. And then consider the associated sub-Laplacian. So if you choose one distribution, which is L1, if your distribution is locally integrable far from the identity element, yes, and for some theta between 0 and 1, you have that the kernel and the operator satisfy these two conditions. Check that the first one is the replacement of the Fourier transform conditions in the theory of Fefferman and Stein. This is a condition in terms of sub-Laplacians. This is the replacement of the Fourier transform condition. And you have this smoothness conditions for your oscillating kernel, then the conclusion is that your operator is bounded from the Hardy space into L1. This generalizes the result of Fefferman and Stein, and that your operator is bounded on LP. Okay, I think that at least in the case of non-invariant operators, these were all the results that I wanted to discuss today. There are also similar results in the case of pseudo-differential operators, also for graded groups and for big groups of polynomial growth. I can give you some references. If you are interested, you can email me and I can share with you the references about this. So in the case of pseudo-differential operator, we prove some estimates in the case of company groups and in the case of gradedly groups, following this approach, the approach of one global symbol, like the one defined by Ruchansky and Turunen, and another defined by the Veronique Fitchen and Michael Ruchansky. And we have some theorems also, maybe more technicals in the case of pseudo-differential operators, but I just wanted to be concentrated today in the case of convolution operators that are this kind of results. So thank you very much.
Okay, thank you, Duvan. Now, please, questions. If somebody wants to put questions or make comments, remarks. Duvan, I have a simple question. Since you have the boundedness of some singular integral operators on this convolution type operators, can you make conclusions about Fredholm properties of corresponding equations?
Fredholm properties, you mean?
Fredholm properties, I mean invertibility, solvability of equations and such.
Yes. I think one can give a priori estimates.
Yeah, there is direct way, I mean,
yes.
behavior of symbol, yes.
Yes, because, for example, in the case of the Laplacian, if you take, for example, sorry for taking this specific example, yes? The Laplacian of U equal to F, where the Laplacian is minus the sum of squares, yes?
Yeah.
And assume that you have then, just let me now write this in the following form.
Yeah.
Just to make one a priori estimate, yes?
Oh, here.
Let me compose, yes, let me compose with this operator or with this operator. Yes, so I think that this is a classical example, but I think that this is related with the invertibility like you mentioned. Maybe not in a direct form, but this is one of the classical, yes, examples. And then that one have here is that you can use the LP boundedness of this operator to give you a priori estimates. Yes. In this case, for example, if you compute the LP norm of this function, that you will have is this inequality. Yes. On LP. Yes, but this is exactly, you see, this is exactly one pseudo-differential operator of order 0 of one convolution operator in the sense of Calderón-Zygmund. Yes.
Okay, thank you. Further questions, if you have some? No? Then thank you, Duvan, for this interesting talk. And you have much more results, but you presented only the simplest ones. I mean, about singular integral operators and not about pseudo-differential.
Yes.
Okay.
Yes. Thank you very much.
Yeah, thank you. Well,